Okay, chapter 23, it's on electric potential. What we'll start to talk about in this chapter is the potential energy that we can have due to charges, very similar to the gravitational potential energy we had due to having some mass and some height. So we'll talk about this idea of having electric potential. This is also going to be the concept of volts, or voltage, if you will. So we'll talk about electric potential due to groups of charges, surfaces that have a constant potential across them, all in relationship to electric potential. And lastly, there's a relationship between the electric field, which we're already familiar with, and the electric potential that I'm introducing in this chapter here. Now let's talk a little bit about this concept of electric potential energy. Think back to having an object, say a baseball, in a uniform gravitational field. Suppose we wanted to move this baseball from point B up to point A. We have to do a little bit of work to this, where work was the integral of the force dotted with the displacement. In the case of the baseball, the force is going to be the mass times the gravity, and the displacement is going to be this displacement from B to A, which is going to be h. The amount of work that we had to do was equal to the mass times the gravity times the height. That work is stored in the form of potential energy. If you let the baseball go, now it can fall and it can do something. It can transform that mass times gravity times height into velocity, 1/2 mass velocity squared. Turns out, and the key concept here is that it's going to be path independent. It doesn't matter whether you go from B all the way up to A, going in this funky little path right here or this path right there. The only thing that matters is the height, the difference between B and A. Same is true if we consider taking a point charge and putting it in a uniform electric field. Keyword being uniform, is if you have this charge and it's at point B and you move it up to point A, the work is still going to be the integral of force times ds. Force is going to be equal to the charge multiplied by the electric field. The distance between B and A, we'll call that d rather than h, just to differentiate it. We can say that the work that was done is going to be the charge times the electric field times the distance, and much like with the case of the baseball, this work is stored in the form of potential energy. If you let this charge go, then it's going to be repulsed or attracted to one side or the other. Now, it is a little bit different than in a gravitational field in that we can have positive or negative charges. In the case of gravitational field, we always have positive mass, we'll never have negative mass. And so if you think about two parallel plates with a positive plate up here and a negative plate down here, we know that the electric field must flow from positive to negative, so it must flow in the downwards direction here. Now suppose we take a positive charge and we move it from point A here to point B right here. It has moved in the same direction as the electric field, therefore the potential energy has decreased. If you think about it, right here it's experiencing a very large force away from that positive plate. Down here it's experiencing a much smaller force away from that plate, and so it has less potential to do something. Similarly, if you move it against the electric field, you take the positive charge and you move it up to point B right here. Now it feels a much larger force away from these positive plates, and so it has more potential energy. It's going to spring away from that positive plate with more energy. The opposite is true for a negative charge. Suppose you have a negative charge right here, and it's feeling a force of attraction towards that positive plate. Again, the electric field is going to be going this direction right here. If you take this and you move it back to point B right here, it's going to feel a much larger force from the negative plate over here. It's going to have more potential energy, kind of like pulling a spring back, if you will. And you can also convince yourself, if you take a negative charge and you move it in the opposite direction as the electric field, the potential energy is going to decrease. So we've talked about the work done, or the potential energy gain, for a uniform field. Now let's talk about it for 2 point charges. So we're going to have a positive point charge we're going to take a little test charge Q0, and we're going to move it, say, from A to B. How much work was done, or better yet, what is the change in potential energy for this guy? Well, that's simply going to be the integral of the force dotted with dl. As I said in the last slide, I said ds, but dl is more appropriate for this diagram. It's kind of drawn out schematically here, where we have our positive test charge, and it's putting out an electric field that's going to be in the radially away from it. And we're going to take our test charge and we're going to move it from A to B, so we kind of see a dl. The radial component is just going to be this component in the dr direction. The angle between them is phi. So really we're looking at the integral of the force multiplied by dl cosine of the angle in between them. The angle in between them is actually going to be phi, not theta. So cosine of phi. Now you can kind of look at this triangle right here and say, well, dl multiplied by cosine theta is simply going to be dr, so that's going to be the integral of the force multiplied by dr. So the work, or the change in internal energy, is going to be the integral of the force. The force is going to be k multiplied by the charge multiplied by the test charge divided by the radius squared multiplied by dr. And we can pull out the constants k, q, and q naught, and the change in internal energy, I'm simply going to write that as the potential energy of the system, is going to be the k multiplied by the charge multiplied by the test charge. Integral of 1 over r squared dr is going to be negative 1 over r dr. I'm just going to simply write that as r. The book is kind of loosey-goosey with that minus sign. Really, it depends on whether we're talking about positive charges or negative charges, and we have to use our knowledge of physics to decide whether the potential energy went up or down. So in general, we can write the electric potential energy between 2 point charges as k q naught q divided by r. So that's the important takeaway equation for this slide. Now, what I was doing on the last slide when I went from the change in potential energy to the potential energy was really I was setting the potential energy when points are very far apart, infinitely far apart, to be equal to 0, much like what we did when we talked about gravitational potential energy. Now, so this is the equation for the potential energy between 2 point charges, and like I said in the last slide, we have to use our knowledge of physics whether the potential energy is increasing or decreasing. So here we're kind of plotting graphs of potential energy as a function of radius for when charges have the same sign and when charges have opposite signs. So if you think about having, say, a positive point charge as well as a positive test charge, as we move the test charge towards the positive charge, it feels a force away from that. We have to do work to force that positive test charge closer and closer and closer to that positive charge. Therefore, the potential energy between them is becoming larger and larger and larger, and it can spring away at a much faster speed. The same is true if both the charges were negative. If the charges have opposite signs and we're moving the point charge towards, or the test charge towards, say, a positive charge, well, that negative charge feels a force of attraction towards that positive test charge. So really we have to keep it from rushing towards that. Therefore, the work done is going to be negative, and the potential energy will also be negative in this case where the charge and the test charge have opposite signs. For both of these scenarios, though, we use the same equation. It's going to be charge times the test charge times the constant k divided by the distance between them. It's just whether it's going to be positive or whether it's going to be negative. So the formula doesn't change, just the sign does. So the nice thing about talking about the potential energy is very similar to talking about gravitational potential energy, is that it is not a vector, it's going to be a scalar. So if we consider the potential energy of this point charge Q0 due to Q1, Q2, and Q3, then the total potential energy is going to be the sum of these three guys, U1 plus U2 plus U3, which is simply going to be K times the test charge multiplied by Q1 divided by the radius 1 plus Q2 divided by the radius 2 plus Q3 divided by the radius 3, where I've simply summed up all these potential energies. Now, if you recall from 241, our energy is always going to be conserved. It must always be conserved. So we can write something like, if we have some total potential energy, all of that could say go into kinetic energy, where kinetic energy is going to be 1/2 mass velocity squared. We can say, how fast would this charge be going when it's really far away from all of these three charges, when all of the potential energy due to electric potential has been converted into kinetic energy. So a little bit of physics 241 coming back at you. So now we're going to take this concept of potential energy that we talked about on the last couple of slides and talk about something called potential, which is very different than potential energy. We'll talk about electric potential, also might know this as voltage. Essentially, potential, or voltage, is going to be the potential energy per unit charge. So we're going to say the voltage is going to be equal to the potential energy per unit charge. Essentially what we're doing is we're taking the test charge out of the potential energy. Much like we took the test charge out of the force to get the electric field, we do the same thing to talk about potential or voltage. Very frequently we talk about the potential difference between 2 points. So we might say the voltage potential difference between A and B. Let's have a subscript AB is going to be the voltage at A minus the voltage at B. Thinking about the units of potential, I've already said that it's going to be a volt. It's going to be a unit of potential energy, a joule per coulomb. We can think about this potential or voltage as two ways. We can think of it as the work that's done by the electric force to move a unit test charge from A to B, or the work that must be done to a unit test charge to slowly move a unit charge from B to A against the electric force. Since this voltage or potential is going to be equal to the potential energy divided by the test charge, that's simply going to be equal to the constant K multiplied by the charge that's causing the potential energy divided by the distance r. One thing to be kind of careful with is now we're going to be talking about potentials or voltages, and we probably are also going to have velocities, lowercase v, running around in some of these equations. Keep in mind, voltage potential is going to be an uppercase V, velocity is going to be a lowercase v, and I'll put a little bit of a tail on mine here to try to distinguish between the two of them. Again, just be careful with voltages versus velocities. Much like when we talked about the potential energy, the voltage is going to increase or decrease whether we're moving towards or away from a positive charge or a negative charge. All of this really boils down to the fact that we're always assuming that Q0 is going to be a positive charge. Now, the book talks about this is if you move in the same direction as the electric field, the electric potential is going to decrease, and if you move opposite, the potential is going to increase. I tend to think of it a little bit differently. I tend to say, I know that positive is going to be associated with high voltage. I know that negative is going to be associated with low voltage. And so am I moving towards a positive charge or moving towards a negative charge? If I'm moving towards a positive charge, then my voltage is going to increase. I'm also moving against the electric field. If I move, say, away from a positive charge, the voltage is going to decrease. I'm also moving with the electric field. Similarly, if I move towards a negative charge, moving with the electric field, the voltage is going to decrease. And if I move away from a negative charge, I'm moving to regions of higher voltage, so the voltage is going to increase. The nice thing about the electric potential is, much like the potential energy, is it's going to be a scalar quantity. So what that means is we add it up like scalars. We don't add it up like vectors. So what we want to do is, if we were interested, say, in figuring out the voltage at A due to 2 point charges, Q1 and Q2, that's simply going to be the voltage due to charge 1 plus the voltage due to charge 2. We don't have to add them vectorially like we did for the electric field for a similar setup. So we could simply write the voltage at A is going to be equal to K times the charge 1 divided by the radius 1 plus K times the charge 2 divided by radius 2, where we know the Q1 is and Q2 is going to be positive and negative 12 nanocoulombs respectively. Since we're looking at point A, it's a little bit closer to the negative point charge than it is to the positive point charge, so we would expect our voltage to work out to be negative at the end of the day. So we can write the voltage at A, it can be K, 9 times 10 to the 9th. Q1 is going to be positive 12 times 10 to the negative 9th coulombs. The radius 1, that's going to be this guy right here, 0.06 meters. Voltage, we don't square that. So plus, we're going to have again K, 9 times 10 to the 9th. Charge is now going to be negative 12 times 10 to the negative 9th. The distance to charge 2 is going to be 4 centimeters, so 0.04 meters. Again, we don't square this guy. And at the end of the day, the voltage at A is going to work out to be about negative 900 volts.